Welcome to the Water Resources Podcast. I'm your host, Bridget Scanlon, from the Bureau of Economic Geology at the University of Texas at Austin. This podcast is produced in partnership with the National Academy of Engineering. In this podcast, we discuss water challenges with leading experts. I would like to welcome Chaopeng Shen to the Water Resources Podcast. Chaopeng is a professor at Penn State University and leads a group called Multiscale Hydrology, Processes and Intelligence. His group focuses on data-driven and process-based models to support decision-making across multiple scales, from catchment to global scales. And applications of his work include rainfall runoff routing, ecosystem analysis, and water quality modeling. Thank you so much, Chaopeng, for taking the time today.
Thank you very much, Dr. Scanlon. I'm very pleased to be here. Also, I would like to say thanks to Dr. Alex Swen, who connected the dots.
Right. So in this podcast, I hope we will discuss basic parameters used in artificial intelligence and machine learning and deep learning within the context of hydrology. And Chaopeng will help us define various terms, describe different approaches, and discuss various applications in hydrology and environmental science. And then finish by discussing path forward and workforce development likely.
Awesome. Let's get started.
Right. So, Chaopeng, you have been in this field for many years now, and I hear from the community a lot of different things about AI and machine learning, and we see it in everyday life. I mean, I took an Uber recently, and he had it an automated pilot, so
Rescue.
Yeah, self-driving electric vehicles. Everybody has a smartphone, and a lot of people are using ChatGPT. Even my next door neighbor, who's a realtor, was telling me she's using it.
Very useful, huh?
Yeah, so it helps us in all sorts of ways. And you have been at the forefront of the application and incorporation of AI/ML into hydrology. Maybe you can describe a little bit what that has been like for you and how difficult maybe it was initially.
Yeah, that's a good point to start. So I was a process-based modeler by PhD training, and that was getting into my third, almost the fourth year, actually third year of my tenure track clock, when I heard about this fascinating technology out of AI that can beat the traditional methods across many different competitions. That I got intrigued, and I started looking at this. And the thing that struck me the most is that these models can actually get trained to perform certain functions completely without the supervisions of human. So that's fascinating to me, because that means, in a way, we can. It sounds something like a reset opportunity for us to re-examine our assumptions without strong human bias. So that's kind of was why I got into this. So when I got in, it was a much different world than it is today. So TensorFlow wasn't even published. And we started working with this esoteric language called Lua. That's the first version of Torch. I actually convinced my students, we learned Lua together. And the first version of our LSTM was actually implemented in Lua. So we wrote this LSTM to model soil moisture. And it took us almost like 8 months, and we were going nowhere, because it wasn't exactly clear what you can get out of this, and wasn't exactly clear what the goal was either. But I think that the goal to me back then is, I think we can improve the predictability, and indeed, it almost took us about 8 months when we started to see some results. So that 8 month was somewhat of a torture, but I'm glad that we made it out of that.
Yeah, so that's nice to hear. I mean, now we feel like we've always had it, it's like the hedonic adaptation in economics, once you have it, then you think you've always had it, but it wasn't so. And so it has evolved. And that was probably like 2017, 2018 time period or
That
later.
was that was around 2016. Yeah, when we started
2016.
to get results. So our first paper came out to 2017.
Right.
Yeah.
Looking
And
at soil
I
moisture.
started to
Yeah.
just started to write papers and proposals. I mean, the initial few ones, we would obviously run into a lot of questions, which are good questions, and there's some concerns, are legitimate concerns. So we've been trying to address those along the way.
Right, right. So maybe we can back up a little bit, Chaopeng, because maybe some of our listeners may not be familiar with some of the terminology that's used in AI/ML. I mean, we use artificial intelligence and machine learning as if they were interchangeable terms, but Alex Sun wrote a very nice review article and kind of defined some of these terms. And I guess the definition he gave for AI was use of computers and machines to imitate human-like behavior. And then he mentioned that machine learning is considered a branch of AI that aims to train machines to learn and act like humans. And then deep learning, which came along in the mid-2000s, refers to a newer generation of machine learning algorithms for extracting and learning hierarchical representations of data. So I think, it's maybe a little nice to have a bit of background and when we're talking about these things so that the listeners can understand where we're coming from. Do you agree with those definitions, Chaopeng?
I mostly agree. And deep learning was mostly about this deep neural networks, which have large depth and huge capacity to these neural networks. And they were supposed to be trained on a massive amount of data set and sort of acquire their functions through training, right? It's like you started with a blank slate and it gained all of its functions through learning from data. However, the AI, I think the concepts of AI keeps evolving. To me, when we talk about AI and ML nowadays, I start to think of AI as more advanced machine learning and as entities that actually have some kind of intelligent, really like human-like behavior, like what Dr. Sun said. So, for example, the self-driving cars you mentioned, or the ChatGPT, or these large language models that really start to exhibit some intelligence, right? So I would say we can go by the textbooks, but sometimes people, when they say AI, they're referring to a very intelligent system.
Right, right. And I guess, some reasons for a lot of emphasis on AI/ML these days is because we have what people call big data. And so some people say, well, what are big data? And I guess Alex's review from the National Institute of Standards and Technology, the NIST definition was like the high 5 V's associated with big data: volume, variety, velocity, and veracity, and variability. So maybe you could just chat briefly about some of those parameters, Chaopeng.
So volume is obviously you have to have a lot of data, but there's also got to be a big variety, and that's also important, right? So repeated data that does not carry much information is not as useful as data that carries a huge variety of information, because the model learns to look at, hey, when one input change, you have a response like certain response, right? So through many different kinds of combinations, the model gradually learned what this one input really means. So that variety aspect is quite important. Then the velocity is, I think, regarding how fast you can, to me, it refers to how fast you can train the neural network. And if that is too slow, obviously it's not very functional, right? Veracity is talking about, I think, the accuracy of the data, the truthfulness of the data.
Right, right.
Yeah.
So we have a lot of different types of data these days, and I mean, even in hydrology, we are using, monitoring data networks and model data. And then also we're starting to incorporate more social science data, and that may come in the form of tweets for flooding or other things. So trying to merge all of these and harmonize them is a real challenge, and to make them useful for forecasting and prediction and stuff. So interesting times, and more stuff that we have, the more we have to do with it.
Exactly. Like you said, there's unstructured data, and you can you apply different kinds of models to it, or you can apply pre-processing techniques. So yeah, interesting times.
Right. So unstructured data would be things like emails and videos and, crowdsourcing data and things like that. That, we can't afford not to look at all types of data when we're trying to constrain and understand what's happening for example, in a flood event or something like that. How do you react to people who say, well, AI ML, it's just statistics, there's nothing new, it's just basic statistics, or others, make comments like, oh, it's a black box, we can't interpret, we don't know what the causal relationships are. But then others acknowledge that they feel like it's transformative. How do you respond to people who kind of diss it?
So I think that's a great question to expand. I want to say that first of all, in the future, with the way I see it, it's not going to be a fancy technique. It's actually going to be like an everyday infrastructure. It's like an operating system, how we interact with data. It's like the cell phone that you use every day. It's going to be very, very common. There's nothing cool about it because you got used to it. Right? So that's how I see this. Secondly, I think it's even the current AI, they're way more advanced than statistics. In fact, there's a funny thing that some students would say, you can learn AI without knowing much about stats, right? Because the fundamental stats they use are at the user level are quite limited. But the statistical equations, in my mind, it can model no more than second or third order of the data, right? And you have multiple dependencies, and that could be complicated enough. However, the AI can really simulate highly, highly complex interrelationships, these joint distributions like our human face, right? So how does AI, generate an image of a human face? And there's all these different correlations between the colors of the eyes and, what that means for a race and, for our facial construct. So those are highly complex interrelationships that AI can capture, and I don't think it's even possible to begin to describe those things with stats, right?
I think the other aspect I was suggesting, some people say it's a black box, and they are a bit allergic to that, So
yeah, from now, I do not see it as a black box. There's a lot of things start to make a lot of sense. Because you can have a generic architecture that gets all of its functions from data, but I think it's not very productive to think of it as a black box. In fact, you should see it as a very transparent box. I think the most productive way that I see it is to see it as different genes. Think of the AI as a collection of great modeling ideas surrounding learning theory, right? A collection of related ideas, and each idea gives you certain behavior, and that's a good gene. For example, one of the ideas is that you have to learn from big amount of data so that relationship you learn is transferable, it's robust, right? That is a good gene. So to support that, the other gene that I would say would be like differentiable programming, because that's the only way you can model a complex relationships and train it in a reasonable amount of time. So that's a good gene. So once we see these different genes, we can take them and use them and recombine them in different ways that we like. So that's how I perceive AI right now.
Right. I mean, I think an understanding of basic statistics wouldn't go awry, because when I hear about some different algorithms in machine learning or deep learning, they're somewhat analogous to some types of basic statistics like principal component analysis or
Right.
clustering
There's definitely a
analysis.
strong linkage there. I agree.
Right. So understanding that statistics, but statistics oftentimes has a lot of constraints, and assumptions and stuff, and so it seems like AI stuff is just doesn't have many of those constraints, so it can come up with ideas that we might not have thought of. I think maybe early on with AI stuff, there was a lot of emphasis on image recognition, like you were talking about the facial attributes and stuff like that. Then in hydrology and environmental aspects, we use image recognition, I guess, for satellite data and remote sensing, land use change and all that sort of thing. But then another aspect would be time series analysis and prediction. Maybe you can, and you mentioned earlier LSTM, long short-term memory. Maybe you can describe those two aspects of AI.
Absolutely. So these are the two prototypical applications I think that the newcomers should get familiar first, right? So the first one is image recognition. That's actually the OG deep learning. You essentially would have these convolutional neural networks, which are built to read an image and tell you what that image is about, or identify certain pixels on that image. This is called segmentation, where it marks out certain regions on the image that belongs to a certain object. And you can already find massive amount of applications with this convolutional neural network. For example, in remote sensing, this is very similar to the OG image recognition, right? So they use this method to identify land use or objects, landslides or solar panels from satellite images. And in fact, they can borrow these trained networks, the networks that were pre-trained on like everyday pictures, these images that people take with their phones, and they can transform knowledge from that model to a satellite image recognition or a satellite segmentation model. So that transfers relatively easily. So I think that's one prototypical application. I've also seen colleagues from Switzerland who uses this technology to IAWAC in Switzerland, who use the technology to identify like microorganisms that they have a microscope, they take pictures, and they have these microbes that flows through, and they identify what these microbes are. And then after a certain amount of counting, they know, what's going on with their water quality, right? So those are all very beneficial applications. The second one is time series prediction. And this is based on like a primary task that hydrologists were tasked to do, which is like predicting these hydrological variables, how they evolve over time, right? So regarding these two, we do have like tutorials online to help people to get into this. With the long short-term memory LSTM, it's essentially a self-trained memory system. After it has seen enough data, it essentially learns a response function of either soil moisture or stream flow or water quality variables to the weather forcings and to the landscape characteristics, right? So after you train with a lot of data, it learns how, for example, soil moisture responds to rainfall, right? When there's a rainfall, soil moisture rises. So it captures those patterns and can predict such variables. And LSTM is really the first deep learning model that the hydrologic community got very familiar with. But you can also do transformers, although in our benchmark, on a benchmark that we've run, it's very difficult to beat LSTM. But of course, I think when the problem is structured differently, the results might change. And when we work with LSTM, there are some benchmark problems. For example, a soil moisture benchmark problem that we provided in our tutorial, and you can try different algorithms on it, where it actually takes the soil moisture that's measured around the world by a satellite and you have also rainfall data that you collect, then you try to capture their interrelationships. It could also be in situ data that's thrown in. And the other is like a stream flow data. There's a CAMELS data set where you have, about 600 basins across the United States, really like, and we actually have this big data over US, right? This USGS collects like 9,000 stations, and the whole world maybe has 40,000 stations. So with that data, we can train the neural network, the LSTM or whatever neural network they're using, to predict how stream flow respond to rainfall, and that is a very useful application in terms of stream flow forecasting, like flood forecasting or drought forecasting. And nowadays we also have more advanced versions with these hybrid models, but the LSTM was a really good entry point.
Right.
No,
go ahead.
Of course, now in the current climate, you can also try to play with some generative models that gradually there are people in the community that started doing that.
Right. So that means generating models that just from data, right?
So generative models would actually generate some, for example, time series based on certain information you tell it.
Okay. So I think sometimes maybe we're not aware of how AI is being used, but I think the Landsat data, had a lot of issues with cloud coverage, and so now they can correct those data and use AI to do that. So I think that's really nice. And then you talked about time series, and you were talking about stream flow, but then I think some of your other work, then you incorporate maybe temperature data and other data then to constrain it and to improve the forecasting. Is that correct?
We found that a lot of the water quality parameters, such as water temperature and dissolved oxygen and nitrate, these are actually some effort led by some collaborators, but we provided some technical assistance. We learned this together, right? We find that these water quality parameters are actually very well captured by LSTM. Like if you're talking about water temperature, for example, the performance was like perfect. Actually, the name of our paper was like exceptional performance, and really is. It's like R square of 0.99, 0.997. I would check ourselves many times before we publish those metrics. So it's amazing how well it works.
What did you start off with then? You had stream flow data and you had temperature data, and then maybe explain a little bit about what you actually did.
So for example, water temperature, it's structured very similarly. The input is the weather data, the ordinary precipitation, temperature, radiation, stuff like that. And then you also have some characteristics of the watershed. If you're trying to model, for example, we would have a slope, soil texture, stuff like that characterizes why a basin looks differently than another, right? And you put these all into LSTM, and the target data is the time series of soil moisture, or actually the water quality indicators. But it's very important that we would train such a network over hundreds of sites together, and this is very important. If you train it over one basin, you get somewhat of a faulty model because it's overfitted to that data set, right? And so learning across these sites is critically important.
Right.
So after you train it and then you plot the time series and you compare with the observations. Of course, sometimes the model is overfitted. It has some of these faulty or artifact fluctuations, so we can add some regularizations to control that. And we can also, some people also try to run like multi-objective predictions, where the same model is trying to predict multiple species. And that seemed like some people reported some benefit, some reported no benefit, whatever. That's a beneficial thing to try at least.
Right.
And you can also use one to predict the other. In fact, I would be interested to see how attention models can be used in this kind of scenario.
Right. So another aspect of working with these data sets, some of the machine learning algorithms are use supervised learning or unsupervised or weakly supervised. Maybe you can describe those a little bit, and they're correlated then in fundamental statistics, the proxies or whatever.
That's correct. The AI community has annoying amount of jargons, and that's very confusing to newcomers. And I spend a lot of time learning about this, and as I get started, so I'm happy to discuss them. However, I think these are actually one of the good genes that we need to inherit and sort of kind of recombine into our domain per se. So supervised machine learning is essentially learning a mapping relationship, right? From some input X to Y, right? That's supervised machine. You tell it what Y is, right? And that relationship can be highly complex. You can give it a deep neural network, you give it transformers or whatever. You can give it as simple as a random forest. When you have like a attribute-based data, right? So some attributes, typically low dimensional, 40, 30 attributes or 12 attributes that leads to one or two outcomes. You can do random forest. You don't necessarily have to do deep neural network. You can also do like boosted regression trees. So that's supervised machine learning, and we've been doing this for a long time. Unsupervised machine learning seeks to dig the patterns in the data, tries to see how the data is organized. For example, the simplest algorithm here would be something like principal component analysis, right? So we're trying to find out what is the direction that can explain the most variance in the data. So in a way, that direction captures the main variability, right? The main direction of change. However, in the age of this AI, the weakly supervised machine learning is even more interesting. So in this setup, this is essentially how you train things like ChatGPT or BERT, these language models, where you have a super complicated neural network. It is forced to kind of fill in the gap or predicts the next token, right? That can be interpreted as one particular form of filling a gap, right? So essentially, there's no differentiation between X and Y anymore. There's only X, right? There's only a set of input. And you can be given a long series of input or a lot of a long series inputs with some gaps in between. And the model is forced to leverage what is provided to it to fill in the gap. What is missing. So this is called a weakly supervised. Well, weakly self-supervised, actually weakly supervised, because it's essentially trying to force the model to capture the internal distribution patterns, what we call the joint distribution of data, right? In fact, that just this simple task gave rise to something as powerful as ChatGPT, and the fact that this happened was purely amazing. Right. I think in the field of geosciences and hydrology, we have done a lot of supervised machine learning. We have done a decent amount of unsupervised machine learning, but still we're just getting to really trying to understand how to leverage this weakly supervised paradigm.
So, I mean, when you mentioned supervised, you have a training data set. So do you think rainfall runoff modeling would, so the rainfall could be the input and you train it with rainfall runoff data, and then you predict the runoff? That could be an example of supervised.
Exactly. So when you have rainfall, temperature data, and the outcome is stream flow or soil moisture, that's a clear supervised machine learning problem. And for unsupervised or weakly supervised, you don't have this clear identification of X and Y. I can give you any part of the data. So let's just say you merge your rainfall and your weather data and the soil moisture data. You merge them together. They form one vector called X, right? So you can mask a certain portion of it. So I can ask you a question in reverse. Essentially, I say, I observed this soil moisture pattern. Can you tell me what the rainfall is? So as the model learned how to fill in the gaps, it should know how to answer that question. Of course, sometimes the question was ill-posed, so it doesn't know what to answer. Actually, those ill-posed problems turned out that in this case, the AI would be able to give you lots of different realizations of it. Just like this is very similar to when you ask ChatGPT or these AIs to give me an image of what my son likes the most, ninja, right? So every time you ask it, it gives you a different image of ninja because that problem, in a way, it's ill-posed, but that means there's like infinite possible answers to that question. You give it a crude hint, it leads to a lot of the different refined responses. So we can do something similar in hydrology, although we haven't really done too much in that direction yet.
Well, I mean, maybe we haven't applied weekly supervised learning very much in hydrology, but certainly I know my colleagues, I see a lot of ChatGPT you can see everything is pivotal or heightened or nuanced or you
Yeah,
begin to recognize the words that it uses quite frequently.
yeah. And honestly, I think this is also where the definition of trying to make the machine do something similar to what humans do is going to diverge from AI because the AI is going to clearly do something that humans cannot do. You know, it generates so many fascinating images and with very abstract instructions. Some of these images humans are it's a challenge of humans to come up with, right? So it's gonna become maybe more and more fancier.
Right. And you know, I was surprised last fall when I broke my wrist at the airport when I was supposed to be going to Australia. And then I couldn't type very well. So then I was using the language recognition part of the computer. I was very impressed with it. I thought it was really amazing, you know,
Well,
how
it was. I mean, in the beginning, I thought it was just like a parrot that knows how to parrot what I'm saying, but it's not. It's actually really like a thinking machine. And I thought, you know, in the few first sentences that I asked it to write, I thought, gosh, it writes so appropriately and so gently, and even got some of these subtleties of how humans respond to certain questions, right? It got the whole picture. It's really amazing. Although now I feel like, you know, after some use, I feel like it's not there, you know, for writing anything serious, it doesn't get the depth. Not yet.
but it might get students over writer block and things like that, you know. So I
Well,
think
I think, you know, eventually this is like sort of going to be our operating system. It's kind of unavoidable,
right.
but I think as I tell my students, you actually I don't want them to use it when they learn stuff because the AI gets trained, they did not. Also, you know, still, I think we should try to, you know, write a lot of things ourselves so it express our own feelings, not some what the feelings of AIs, right?
Right, right. So, I mean, if we go back a little bit, you know, the hydrologic community is traditionally using a lot of process-based modeling to understand what's going on. It's constrained by theory, and they have input data, and they calibrate the models, and they have parameterization, and then they get the output, whether it's stream flow, groundwater levels, or soil moisture, or whatever. So, but there are a lot of, you know, limitations to process-based modeling, and maybe AI can overcome some of those limitations. And sometimes people think it's like either or, it's process-based modeling or AI. But really, I think maybe the strength could come from some sort of hybrid, like we think about, you know, energy transition, you know, a fossil fuel car or an electric vehicle or a hybrid, you know. So,
Yeah, and that transition can take a long time.
right, right. And so maybe
And
we can help the transition by, you know, using AI to parameterize process-based modeling, incorporating process-based modeling into AI like you are trying to do. So maybe you can describe some of those linkages and how you see it evolving.
right. So before I dive into that, I would like to say that sometimes when we examine how the world changes, if you look from the side, it seems to be going in circles. It seems to be coming back to the same place. But if you actually, if you look at it from above, it seems to be going to the same place. But if you look at it from the side, it's actually doing helix. You know, it's spiraling up because every time it comes back, it's actually a different context. Okay. So this is going to rhyme with some of the things I want to discuss. So regarding there's a lot of limitations to our original process-based model, but there are also something good about them. I'm going to come to the good ones later. So I think the many challenges. The one significant challenge was bias, because we have certain assumed structure of the model, but when the model has a structural bias or certain deficiencies and just doesn't behave in the way that nature behaves, you're going to see a bias in your model results. It's almost like when you try to put the chairs together, but one of the legs was longer. So you would, force it, you put it, barely hold it together, but nothing, it's always going to give you a large error. It's always going to be something is off here and there, right? And you force this side to stand upright, and then the other side would, start to juggle, right? And the other thing is we have also have a lot of parameters in the model. And we run into this problem, but not uniqueness, because because of this computational expense and the way we trained our models, we cannot take the model to confront it with lots of data. We typically, the paradigm was to confront it with the data from one basin or a limited amount of basins or sites, right? So you run into this problem where different parameter sets give you the same response, so you cannot differentiate between them. So the uncertainty there was huge. And I remember when I started my PhD, I worked with one of these models at SWAT, and I was like, wow, I could change its parameters in 10 different ways, and they give me the same results. And actually, I calibrated 10 times using different random seeds. It gave me very different results. So I didn't know what to trust, right? And the other thing is, it could also saturate because you're tuning some of the parameters. The learning ability of that model quickly saturates. You learn, and all it can do is to absorb some parameters, right? So those are the limitations, but there's also strength in that. I mean, the process are clear, and it respects a mass balance law. So you have kind of a bare minimum guarantee of physics there. So you take it to a place where there's no data, it can function in a bare minimum sense, right? And also these kind of models tend to kind of extrapolate better. So, but actually for scientists, the most valuable thing is probably that it has full interpretability, and I can understand the whole thing. I can even explain this to stakeholders, right? So that's I see that there's pros and cons. So when we move to in machine learning, it's on the other side of the spectrum, right? The biggest advantage it has is that it simultaneously can learn from a massive amount of data. So the relationship that it learns is robust, right? So we can be more confident in the conclusions that we make. And then it's able to actually compute because of the way that the neural networks are structured, that it can compute very efficiently. And that actually allowed it to grind through all this much data and train a highly sophisticated neural network with large amount of weights. So just on a basic level, like our process-based model, how many parameters do you have? Maybe 12, right? Maybe 20, and that's very high dimensional. But consider something like the LSTM that we trained, right? It has 500,000 weights, and ChatGPT probably has 1 trillion, and Microsoft said they were going to have a model with 56 trillion weights, right? So the orders of magnitude are differed by so many orders of magnitude. And along with that comes the complexity of representing these real world functions and the ability to actually model almost any function, right? To actually absorb a lot of information from data.
Right. So I guess what you're talking about then is the process-based modeling, it's following theory, so we can interpret it and we can understand what's happening. And then we can probably use it more in a predictive sense because we've got the theory. It may be biased, but then a purely AI model driven by data, will come up with some sort of relationship to predict what's going on, but it may not conserve mass.
It may not conserve mass. And
Unless
it
we,
may also
unless
learn
we,
the wrong,
yeah.
sorry, it may also learn the wrong relationship. So it can, actually, this happens all the time. So it can potentially give you the very good results for the wrong reasons. So the sensitivities might be wrong, right? And the reason is in our world, all of the things are covariant, that they're changing at the same time. So when the AI learns those relationships, it's not able to pick up which one is the causal relationship, right? Which one is the true cause, which one is the effect. It doesn't have that physical concept, right? So it could, especially when you take this training model and try to predict in a region or a regime where there's not much data to cover that, then you're likely, it's likely to make mistakes.
Right. But then, it can ingest lots and lots of data and come up with relationships with high speed, I mean, of course, depending
Right.
on your computer architecture. So there are the differences between the process-based modeling and the purely AI model. But then I think some of your work, then you were trying to combine these. Maybe you can describe the differential modeling approach that you are promoting.
Yeah, thanks for the lead. Yeah, so I was actually thinking about the similarity and commonality and dissimilarity between these models. And I realized that the true one thing that is different is this differentiable programming that allows AI models to train massive amount of weights. Okay, so because if you can understand an AI model, let's say supervised machine learning, right? So we're trying to capture some relationship y equals to f of x, right? And we tune some weights to match the observations. But we've been doing this for a long time for process-based models, right? You would have some physical parameters sitting there and you calibrate it. But why is it that the AI models get it much better, right? Much more robust. And that is because it has access to this technology called differentiable modeling, inspired, probably propelled by the progress in AI to assimilate tons of data, right? So with that, you have differentiable programming, which is a way to keep track of information so we can compute the gradients and do back propagation. So the gradients of outputs with respect to inputs inside the modeling chain. And once you have such a system, you can back propagate that whole entire system, the gradient information back through, and you can use this gradient-based optimization to train a very, very highly parameterized neural network. Right, so that is the fundamental technology behind neural networks. And I realize that we do not need the entire package of AI to actually have this key, what I call gene, right? This differential programming being a gene. We can actually take that gene and use along with our process-based knowledge and have all the good things about these from this gene, and also marry it in a way with the equations that we know, with the laws that we understand, right? So we can have the best of both worlds. So I make a joke. It's like when we want a truly a beautiful thing, like let's just say a young boy want to propose to a girl, and he doesn't need to marry the entire family, right? He only needs one thing out of this is so I mean that's a bad joke, but you get where I'm going. You could so the idea back then was to take of course some other domains started doing this as well. So it's to take the differentiable programming paradigm and make our models differentiable. So once our models are differentiable, it can be coupled to neural networks, and these neural networks can serve to model a missing link in the whole chain, right? It can model a missing relationship, and that missing relationship can be either a parameterization relationship, right? So it can model, let's say, how can I generate the parameters that these models need, right? It could also be a missing process, like how does rainfall translate into runoff, right? Or how does let's say, how does the water translate into ET or resistance parameters, right? So we can learn that missing relationship and simultaneously grind through a massive amount of data, and all those big good characteristics can come along as long as you have this differentiable programming gene.
Right. So I understand that you are now trying to apply this in the national water model with the next generation national water model. Is that correct, Chaopeng?
Yes. So that's a grand goal. So we know the national water model is responsible for making flood forecasting around the nation, keeping people safe, reducing damage. I think there's an opportunity to really improve it using this AI technology. So we're trying to incorporate both data-driven machine learning like LSTM and these differentiable models where you have actually neural networks to sort of enhance your process-based models. So in the end, we might get a next generation national water model that is highly capable, very performant. So our benchmarks, we show that these differentiable models, they can be as strong as these purely data-driven models, even better in the data sparse regions. And they can also provide you with this full process clarity. So I think the next generation, of course, we are trying to be one of the candidates for this model, right? So I don't want to oversell what we're doing. But I think that we're going to offer a lot to I would say, the American public or the whole world, something that can much better forecast flood, even in a data scarce region. And I want to add one point to the differentiable programming, the differentiable modeling. So the differentiable models can utilize this automatic differentiation engine that a current machine learning platforms provide. But also you can do it in a different ways. And you can do it using what we call a joint operator, which runs through some mathematics to give you the gradients, or you can do finite difference. Whatever way to provide that gradients would be enough. And the whole point is, once you are able to make this linkage, it's like you're providing a wing to your model. Like it's like what we say, tigers have wings, or you can say that you can actually now connect a huge augmented brain to your own brain. Now you're able to do a whole lot more. So the entry ticket, the ticket to the entrance is this differentiable, the ability to be differentiable.
Right. So, I mean, you started off in 2015, 16, working in these topics. What do you think about the workforce development now? I mean, are we teaching students in colleges the tools that they need to apply these techniques, or is it being? I mean, we have industry doing it. We have a lot of different industries doing it, but I mean, the government agencies, are they taking it up? Is there the workforce there to do it?
In my perspective, I think there's a great shortage of AI education in non-computer science majors, especially in engineering. We need to enhance it by a lot. I think we are not doing what is needed. And a lot of departments around the nation is actually trying to make up for that deficiency. So I think we need to enhance the AI education, not only at the graduate level, which some faculties are trying to do here and there, but also at the undergraduate level. And that's a core deficiency, because the undergraduate curriculum never have this AI education. They learn some stats. I mean, they learn some basic concepts, but they don't really get any actually training to do AI, maybe because they were in engineering. But the pattern is that AI is going to be incorporated as a basic front infrastructure. So the engineering students do need to know that. So I think I see that we need to enhance our teaching at the undergrad level. We need to let the students know that this is important. And I do see some students, they kind of select, and they would think that I cannot do AI. But actually, they didn't know that the AI is probably easier than their fluid mechanics course. Really. So it's something that is actually a generic technique you use and you can apply to all these different domains. It's actually very time-worthy thing to learn. But the other thing I want to comment on is I think I've noticed some lack of diversity in the classes, the classrooms, especially in terms of gender. Because if you check the background, I'm pointing the fingers at them. Okay, so this background, this source major of computer science, there's a huge gender imbalance there. And that resulted from many different reasons, because of stereotypes, because of with some of these readout courses, because some of the preconceived notions that students have, and so I do think that we need to bring more diversity into the classrooms in terms of gender and race, and we can achieve that. Actually, I have a grad student, female grad students, and she does very well. Like she's awesome. Like I don't think there's any way, shape, or form. And I think that there's a lot of work for us to do.
Right. Well, I really appreciate your taking the time to explain some of the fundamental concepts behind AI, ML, and deep learning, and how you got into the field and how it's being applied in hydrology, and how we can have maybe sort of a hybrid car where we're combining process-based modeling with AI to kind of optimize and get the advantages of both. So thank you so much, Chaopeng, for your time. Take care.
Thank you a lot for the opportunity.
Okay, bye-bye.
Bye.